So today we are going to discuss about the procedure for Carter's pendulum experiment, which is a very accurate method of determining the acceleration due to gravity g. Now you can determine the acceleration due to gravity with multiple methods. So for instance, you can use a simple pendulum, but let's say I wanted to use a physical pendulum, like a physical pendulum or compound pendulum, which you see here. Then there is a slight issue in that unless the rod is exactly symmetric, I would not know the location of its center of mass, right? And the location of the center of mass is very important because the distance between the pivot and the center of mass determines the time period of oscillations, and it appears in the relation for the acceleration due to gravity. Now, I will not derive this expression which you see here. The details are given in the manual. So you can derive an expression relating the acceleration due to gravity and the time periods t1 and t2. Now what are these t1 and t2? So if you look closely at this pendulum, you will see that there are two knife edges, one on top and one over here. Now suppose I pivot this pendulum about this knife edge and then I set it into oscillations. Then when it exactly goes through the center equilibrium point, I start the clock. Then I count the time for 20 oscillations. So you'll have to count the number of oscillations, and when it crosses 20 mark, then you stop it. And then note down the time period. So the time which you have determined here divided by 20 will give you the time period for oscillation about this pivot. Let's say I call that t1. Then what I do is, now this is where you have to be very careful because this is a very heavy rod. So you have to be very careful when you change it. Now I turn it upside down and pivot it about the other knife edge. And then I repeat the same procedure. I set it into oscillations and determine the time period. So the time period for oscillation about the other pivot, let's say, is t2, which is what appears in this expression. Now you also see that there is a h1 and h2. Now what are h1 and h2? h1 is the distance from the first pivot up to the center of mass, and h2 is the distance from the other knife edge to the center of mass. Now it's very easy to know h1 plus h2. It is simply the distance between the knife edges. But this expression also involves h1 minus h2, which you will not know unless you determine the location of the center of mass. So there are two ways of doing this experiment beyond this point, which is one uses the fact that suppose I adjust the position of the knife edges and t1 becomes equal to t2, then this entire term drops out. So in that case, I do not need to know what is h1 minus h2. I will simply do the experiment knowing just h1 plus h2, which is nothing but the distance between the knife edges. Right? For that, of course, I will have to do the experiment multiple times and carefully adjust. You can see that there are some screws over here. So here is where you have to use your intuition. So let's say that t2 is much less than t1. So what that implies is, and repeat, t2 is much less than t1. So what that means is that probably the knife edge corresponding to t2 is very close to the center of mass. So you will have to increase that distance, which means you will have to push the knife edge further away. So in any case, you adjust either of the knife edges, but in a sort of systematic manner, such that t1 becomes almost equal to t2. So if t1 becomes almost equal to t2, then this term is negligible compared to the first term. I can simply put it equal to 0, and then I can go ahead and determine t1 and t2, which are actually same now. So this will simply become 2t1 square, and then I know the distance h1 plus h2, so I can determine g. So this is one way of doing the experiment. The other way of doing the experiment is, let's say I find it too tedious to make t1 equal to t2. What I can do is, I can take this rod, there is a knife edge over here, so you can adjust the position of the rod on the knife edge such that it exactly balances. And if it exactly balances, I mean it's in rotational equilibrium, then that means the knife edge is just below the center of mass. So for this you will have to again take a lot of care. Yeah, we are almost there, because if I remove my hand, then it's not perfect. Okay, so you will have to maybe try it multiple times till the rod is in rotational equilibrium. Okay, this is almost it. Right? Yeah, fine. So now, once you have done that, you have located the center of mass. What you can do is mark the position of the center of mass with a pen or a chalk piece. So now, since you know the location of the center of mass, this distance, let's say, is h1, and the time period of oscillation about this knife edge would be t1, and this distance would be h2, and the time period of oscillation about this knife edge, when I pivot it about this knife edge, would be t2. So I will also know h1 minus h2, because I know h1 and h2 individually. I can calculate h1 minus h2, and of course, as you can see from here, h1 plus h2 is simply the distance between the knife edges. So you can do the experiment in two ways. One is determining the location of the center of mass by balancing it on this knife edge. The other is, let's say you don't want to know the location of the center of mass, then the other method is to make the time periods equal by adjusting the position of the knife edges. Okay. You can adopt either of these procedures, but in either case you will have to be very careful while determining the time periods. And one more thing, while determining the time periods, I'll just give you one idea to find out when the pendulum crosses the equilibrium position. Okay, so that is the time when you should start and then stop the time, stop the stopwatch. So the reason for that is, suppose you choose to take the end point as the reference line, then it is going to move very slowly. The pendulum will be moving very slowly when it is close to the end point, so there is more scope for error. So that is why, if you see on the wall, a line has been drawn which corresponds to the equilibrium position, and whenever the rod goes through that, that is the point or time at which you should start and stop the stop. Okay, so that will give very accurate measurements. Whereas if you do it at any other point, there will be much larger error, and that is because it is going to go through very fast. So the error in your time period is going to be very negligible in this case. So obviously this is a very difficult experiment for two reasons. One is, as you see here, there is a caution. You have to be very careful while fixing the knife edges. Make sure that it doesn't slip out. This is very heavy rod and you can even get injured. So don't get very close to the pendulum. Stay away from the pendulum while making adjustments. That is point number one. And point number two is, since you will have to either make T1 equal to T2 or determine the location of center of mass, both of which are very difficult, you have to better repeat this experiment multiple times and get the average value of G. And of course, you will also in that process determine the error in your measurements. So I hope the procedure for this Cater's pendulum is clear. So this is one of the more difficult experiments in this lab. So I urge you to do it with caution and take care while doing it.